yet another object that is called the electric displacement. Okay, so what do we have? So we had the following thing. We had that our rho bound at a certain position. Again, I'm not going to write the position here, but you imagine that there's a chunk of matter whose polarization you know. So once again, right? So this is bound charge. Density. This is polarization. In the bulk, we've got this. On the surface, we've got what we just argued to be the kind of remnant non-compensated charge at the boundaries, which is just the end product of the polarization with the unit normal. So the idea now is that we're going to kind of differentiate two types of electric charge. They're not physically different. It's just that for us, in the settings that we consider, they have kind of a different origin. So the total charge density we write as just rho, and that contains absolutely everything. Okay, everything that has electrical charge in the vicinity of the evaluation point that you're considering. But we're going to say, well, okay, that can have two different origins. It can be, first of all, this bound charge that I have here. I've got chunks of matter in an environment and they polarize a little bit, and I've just learned how to associate that to a residual bound charge density in here. Then you say, okay, fine, that's what I have. But I could also just come and, you know, paste electrical charge onto this additionally to these bound charges. And these are going to be called the free contributions to the charge density. So this is bound charge. And this is the free charge. Okay, maybe this kind of slavery nomenclature needs to be updated one day, but yeah, then you've got a lot of books to change. So the idea is that you're doing your experiment, you've got your chunk of material, you put electrical fields in there, it polarizes and things, and then on top of that, you come with your charges, you kind of add charge into that. The total charge density that you have has these two different origins. The bound charge, which is really inherently some microscopic movement of the constituents of your piece of matter, and then all the rest that you throw at it, you know, that you will call the free charge. The point is that Gauss's law is still valid. Right? Gauss's law is, in a sense, microscopically always valid, provided you take all the charges into account. However, you can actually simplify or rewrite it in an equivalent way. So what are we going to do? So what does Gauss tell us? Gauss tells us that if I just take epsilon 0 times the divergence of E, I'm just rewriting Gauss's law here, div E is equal to rho over epsilon 0, that's my rho. Okay, always valid. But what is this? Well, we just said that this had two pieces, rho bound plus rho free. But we just said that the bound charge is minus the divergence of the polarization. Okay. So divergence, you say, okay, let me actually think that the ones I can really play with are the free charges. These are my handles onto my system. These are the things that I can actually put, remove at will, and therefore they are my true source of all these electrostatic phenomena that I'm looking at here. The polarization is a result of the presence of these free charges, and the electrostatic field itself comes from both the direct field coming from the free charges, but also the field coming from the polarization, which itself comes from the free charges. Okay? So we just are led to rewriting this equation. You see the absolutely profound development we're making here. We're going to rewrite this equation by saying there's a combination epsilon 0 E plus P, whose divergence is the free charge density. Okay? You should be like horribly excited at this stage because this is like really profound. Yeah? And that's our definition for the displacement D, which is this, electric displacement. Okay, by definition. So D is just epsilon 0 E plus P. That's the kind of big conceptual leap. And it obeys the equation that we've just written here. So div D is equal to rho F. Okay, so everything you know about playing with divergence here and whatnot applies to this new equation here. So in particular, if I was to turn this into an integral form, that would work directly. I could just do an integral, use the divergence theorem, turn that into a surface integral. So this thing, it would be Q free enclosed. Yeah, so this is the enclosed free charge. Okay, so we're kind of just like trying to push away the complexities associated to polarizable matter by saying, actually, we're just going to hide them into a redefinition of the object that we're considering. Instead of talking just about the electrostatic field, we are going to talk about the displacement. And later we'll make some statements about how to relate the two here. Okay, so maybe a very quick example. So I have a wire, and this wire here has a line charge density of lambda, the usual symbol that we have. Okay, it's a uniform line charge density. The wire is infinitely long as far as you're concerned, and that's it. However, this is a wire like the ones you have at home. It has a kind of insulating rubber sheet or rubber tube around it. Yeah, so here my drawing talents are really challenged. So I've got a rubber insulation around that thing up to a radius A. Okay. So it's kind of complicated because this rubber insulation, or whatever it is, I'm not telling you exactly how it reacts. I'm kind of just saying it's like it's some form of material that is polarizable. Does that mean that you can't compute anything in there? Well, not really. Okay, and we'll try to see how it goes. So let's imagine that our task is to find D. So what do we do here? Well, we can just use the usual tricks. The trick of Gauss. First of all, I have symmetries in this problem. It's a cylindrical configuration. It is rotationally invariant on the axis of the cylinder. It has no dependence on where I am along the cylinder because I've assumed this thing to be infinitely long. Therefore, any field that comes out of this has to be such that it is rotationally invariant and translationally invariant. Okay. So what I can do in order to determine my field is to use the Gaussian trick that we've done in the past, where I take now a new Gaussian surface, which is going to be, say, first outside. So I imagine another Gaussian cylinder like this outside, and I'm going to consider a certain length like this, and the only field that I can have has to be radially coming out of the axis of the cylinder. Okay. And what I know is that I have the integral form of Gauss's law here, which is just that the integral over any closed surface here of the surface element times d has to be the total free enclosed charge. Okay, so what does that tell me? So let's do that, right? So let's imagine that I've got this this Gaussian surface here, and it's at radius r greater than a, and it has length just L. So this is my definition of the surface S. So I have that the integral dA over S dot D has to be equal to QF enclosed. What is QF enclosed? Well, I've got just L times lambda, right? Because the only place where there is free charge is on the wire. Of course, the presence of charge on the wire induces charge movement inside my rubber. However, this is bound charge. This is not free charge. Okay, so here I'm computing just the free charge density contribution to this. And in this case here, because D is along R, since D is along R hat, this thing here is just equal to the intensity of D at that distance. So D of R with the surface of this Gaussian surface here, which is just 2 pi R times L. Okay, so exactly the usual reasoning. So that's what this gives us. It gives us that D is just equal to lambda over 2 pi R in the R hat direction. Okay. So question for you. Which values of R is this result valid for? I've put my Gaussian surface outside here when I told you, but am I just like being too restrictive here? Huh? So there are possibilities. Is it valid for an R which is between 0 and A? Is it valid for an R which is from A to infinity? Or is it valid for all R? We had clickers. I would ask you to vote now. So who votes for only valid from R is equal to A to R infinity, but not valid for don't be shy. Okay. Who votes for, valid between 0 and A, but not outside? Okay. Who votes for everywhere? You got to commit. Okay. So you voted twice, which is always the safe option. Yeah. So this reasoning here gives you the displacement at all values of R. Okay. This is valid for any R. Because what have I done? We have said that this thing here is valid. We have a local equation. Divergence of D is the free charge. The only place where there is free charge is on the wire. Okay? And therefore, anywhere away from the wire, that is for any R greater than 0, then this equation is valid. However, of course, you have to understand that the meaning of D is different if you're inside the rubber or outside the rubber. Okay? So I'll just get back to your question, or maybe go ahead. So, okay, so first question, how do I know that D is along R? Let's imagine that D has a certain component in the angular direction, and for that matter, also a component in the Z direction, okay? Now, let me use the following discrete symmetry, which is an inversion symmetry along the axis of the wire. I'm taking the wire and I'm literally doing like parity transformation, like this. So I have not changed lambda. I have not changed the free charge distribution. This stays the same. However, if I do such a parity transformation, then this vector that I had that had a Z component and an angular component, it gets inverted. But it's the same configuration. So the only consistent choice is that this particular Z component and angular component is 0. And the radial part, you see, doesn't change under this discrete invariance. So it's a question of symmetry. That's how you know that D can only have a component along the radial direction. Okay? And then your second question was, what is D? Okay? So D, again, is the combination of the local electric field and the polarization. So you see, it's like you're running after your tail here, because where does polarization come from? Polarization comes from matter that reacts to the presence of an electrostatic field. It polarizes. It could be that matter is spontaneously polarized as well. That's also possible. It comes from somewhere, right? But certainly, if the matter reacts to the presence of electric field, its polarization will depend on the field. And this is where you start like lifting yourself up with the bootstrap, because you put an electric field, the matter polarizes. The polarization is an electric field. Therefore, the matter polarizes further. Okay? So the polarization is the absolutely infinite sequence of, in the simplest case, you put an electrical field on a piece of matter. The atoms react to that electrical field. But by reacting, they create their own field, which affects themselves also in how they polarize. And then you get an infinite sequence like that, that has the original cause, cascade of effects until there's a certain equilibration of the polarization. And this is big P. Okay? And what this equation is telling you is that you are kind of back engineering the effect of your original electrical field by taking this particular combination. So let's say that P is proportional to E. Then this equation is like epsilon 0 plus something proportional to E. But then I could it would be like E times 1 plus epsilon. But then the 1 plus epsilon, if I put it back on the other side, is like 1 over 1 plus epsilon. Yeah, and that I can write as an infinite series of terms that correspond to the ones that I was telling you. Yeah, so external field polarizes matter, matter then further polarizes itself by the reaction it has to this. So D, to answer your question in more poetic terms, D is essentially the Christmas wrapping, Christmas box in which you put all these effects, nice little, decorations on top of it, really complicated stuff inside, but from the outside, super simple. It's just that you don't know what the electrical field is. Okay? So D is the simple friend that you have because it's the friendly combination of the electrical field and the polarization. However, it's not your electrical field. Yeah, because it also puts in the polarization effects in there. So it's a convenient rewriting. It's a convenient abstraction. Okay. So here, let's just finish what we wanted to say here. Let's say that my R is bigger than A. Then I'm outside the rubber. So here, right? I'm outside the rubber. And of course, outside the rubber, P is 0. And therefore, I can write my electrical field as just, inverting that equation here when P is 0, right? So E is just 1 over epsilon 0 times D for R greater than A. If R is less than A, you don't know P, and therefore you don't know E. But D, well, if you're like me, you're very happy. Okay? You know D, but you don't know either P or E. But still, that's something. Okay?